I told you that locked inside something, well, a million times smaller than a grain of sand is enough power to light up a city? Or level one,
Yeah,
we're talking about the atom's nucleus. And today we're diving deep into what happens when that nucleus isn't quite so stable.
exactly. This is the deep dive, and our topic today is radioactivity and nuclear energy.
You sent over some fascinating material, really everything from the very building blocks of atoms all the way to the sheer force unleashed in nuclear reactions.
And our mission, well, like always, is to sort of cut through the complexity, pull out the crucial insights,
Right.
and give you a clear, engaging understanding of these fundamental concepts. No need for a physics degree here.
Definitely not.
Okay, so where should we begin? How about the atom itself? Start there.
Sounds good. So picture this. At the center of every single atom is this incredibly dense core, right? The nucleus. It's packed with protons. Those have a positive charge. And neutrons, which are, well, neutral.
And buzzing around this nucleus in these sort of specific zones called shells are the electrons, negatively charged.
Right. And the identity of an element, what makes it, say, carbon instead of oxygen, it just comes down to one thing.
The number of protons.
Exactly. The number of protons, we call that the atomic number Z.
Yep. And the mass number, A, that's simply the total count of particles in the nucleus. So protons plus neutrons. Collectively, we call them nucleons.
And get this, the nucleus is just mind-blowingly tiny compared to the whole atom.
It really is.
Like, if the atom were a football stadium, the nucleus would be, what, a marble?
Pretty much, yeah. A marble right in the center. We're talking orders of magnitude difference. About 10, 15 meters for the nucleus versus 10 meters for the atom. It's tiny.
Wow. And those electrons buzzing around, their mass is basically negligible compared to the protons and neutrons.
Almost entirely, yeah. For all practical purposes, you can say the nucleus holds pretty much all of an atom's mass.
Okay, so we've got the super dense nucleus, protons, neutrons, packed together. But here's where it gets interesting, because atoms of the same element, they can actually have different numbers of neutrons.
Ah, yes. Isotopes.
That's the one.
Precisely. Isotopes are like variations on a theme for each element.
Yeah.
They've got the same atomic number, Z, the same number of protons. So they're the same element, but they have a different number of neutrons.
Which means a different mass number, A.
Exactly. Think of hydrogen. You've got your regular hydrogen, protium, with just one proton, no neutrons.
Okay.
Then there's deuterium, still one proton, but it's got one neutron.
Right. Heavy water.
Yep. And tritium, one proton, two neutrons. All still hydrogen because that proton number hasn't changed.
And carbon's another good example, right? Carbon-12, carbon-13.
Carbon-14, exactly. 6 protons define it as carbon, but they have 6, 7, or 8 neutrons, respectively.
It's amazing how many variations some elements have. You mentioned tin has, what, 10 isotopes?
10 stable ones, yeah. It holds the record. Now, the key thing here is stability. Some of these isotope variations are perfectly stable. They have a nice balanced ratio of neutrons to protons.
But others, not so much.
Others are unstable, often because they have too many or maybe too few neutrons compared to protons. These are the radioactive isotopes. They'll spontaneously change, they decay to try and reach a more stable state.
Okay, so isotopes. Same element, different neutrons. Now, you also mentioned isobars and isotones in the material. They sound similar?
They do, but they're different concepts.
Yeah.
Isobars are atoms of different elements, so different Z, different number of protons.
Okay.
But they happen to have the same mass number, A.
Yeah.
So the total number of nucleons, protons plus neutrons, is the same.
Gotcha. Give me an example.
Sure. Sodium-23 has 11 protons and 12 neutrons, mass number 23.
Right.
Magnesium-23 has 12 protons and 11 neutrons, also mass number 23, see? Different elements, sodium and magnesium, but same total mass number.
Okay, makes sense. Carbon-14 and nitrogen-14 would be another pair then.
Exactly. Both mass number 14, but one's carbon, 6 protons, one's nitrogen, 7 protons.
All right, so different elements, same mass number for isobars. What about isotones?
Isotones focus on the neutron count. They are atoms that have different numbers of protons, so different Z, and usually different A as well.
Okay.
But they have the same number of neutrons.
Ah, okay. Same neutron count.
Yep. Let's go back to sodium-23. It has 12 neutrons.
Right.
Magnesium-24, that has 12 protons, but also 12 neutrons. Different element, different mass number, but same neutron count, 12.
So 12 neutrons each.
Precisely. Another pair is potassium-39. That's 19 protons, 20 neutrons. And argon-40, 18 protons, 22 neutrons. No. Argon-40 has 22 neutrons. Let me recheck that example. Potassium-39, 19 protons, 20 neutrons, and calcium-40, 20 protons, 20 neutrons. Both have 20 neutrons.
Got it. It's all about keeping track of those protons and neutrons. Okay, so we've established some isotopes are unstable, radioactive. How did we even figure this stuff out? It wasn't exactly planned, was it?
Not at all. Pure serendipity, really. Henri Becquerel, 1896. He was working with uranium salts.
Okay.
These salts are fluorescent. They glow after you expose them to light. He thought maybe this glow was related to X-rays, which had just been discovered.
Makes sense.
So he's doing experiments, but then there's a cloudy day in Paris, no sunlight to activate the fluorescence. He puts his uranium salts away in a drawer.
With photographic plates.
Exactly. Wrapped in black paper, mind you. He puts them away together. Later, he develops the plates just, expecting nothing.
And who?
They were fogged, as if they'd been exposed to some kind of radiation.
Even though they were wrapped up and in a dark drawer.
Yep. The uranium salts themselves were emitting something spontaneously, some kind of invisible rays that could pass right through the black paper.
Wow. So Becquerel rays.
That's what they called them initially.
Yeah.
Then Ernest Rutherford, a brilliant physicist, started investigating these rays more systematically. He used magnetic fields, electric fields, to see how the rays behaved. And he found they weren't all the same. There were 3 distinct types.
And those are?
Alpha, beta, and gamma.
The big 3. Okay, let's break them down. Alpha particles first. What are they?
Alpha particles, or I particles. Think of them as basically a helium nucleus that's been ejected.
A helium nucleus, so 2 protons, 2 neutrons.
Exactly. 2 protons, 2 neutrons, all bound together, which means it has a positive charge, right? Plus 2 elementary charges, or plus 3.2 by 1019 coulombs.
And they're pretty hefty, comparatively speaking.
Yeah, relatively massive. About 4 times the mass of a single proton, roughly 6.68 by 1027 kilograms.
How fast do these things move?
Pretty fast, actually. Order of 107 meters per second. So a fraction of the speed of light, but still very quick.
Okay. And because they're relatively big and charged, they must interact strongly with other matter.
Oh, absolutely. They have a very high ionizing power. As they barrel through stuff, they're very effective at knocking electrons off other atoms. Think of it like a bowling ball going through pins.
So they cause a lot of disruption along their path.
A lot. About 100 times more ionizing than a beta particle, and maybe 10,000 times more than a gamma ray for the same path length.
But that strong interaction must mean they don't travel very far. Like the bowling ball quickly loses energy.
Precisely. Their penetrating power is very low. They only go a few centimeters in air, maybe 3 to 8 centimeters.
And stop by paper.
Yep, a thin sheet of paper, even the outer dead layer of your skin, is enough to stop an alpha particle.
Okay. And because they're charged, fields affect them.
Right. Both electric and magnetic fields will deflect them. Though, because they're quite massive, they aren't deflected as easily as, say, beta particles.
And they can cause fluorescence, affect photoplates. Rutherford used them famously, didn't he?
He did. His gold foil experiment, firing alpha particles at thin gold foil and seeing how they scattered, that's what led him to the idea of the atom having a tiny, dense, positive nucleus. A revolutionary discovery based on these particles.
Okay, so alpha. Heavy, positive, high ionization, low penetration. Got it. What about beta particles?
Beta particles, alpha particles, these are essentially fast-moving electrons. We write them as beta C or 1 or no.
Electrons? But coming from the nucleus, how does that work?
It seems weird, right? They aren't just sitting in the nucleus. What happens is a neutron inside the nucleus actually transforms into a proton. To conserve charge, an electron, the beta particle, is created and instantly ejected. And technically, an antineutrino is also emitted to balance the energy and momentum books. But the key thing is that electron popping out.
So a neutron becomes a proton, spitting out an electron, much lighter than alpha particles.
Oh, yeah, much lighter. Same mass as any electron, 9.1 by 1031 kilograms. And they carry a negative charge, negative 1.6 by 1019 coulombs.
And faster.
Significantly faster, typically order of 108 meters per second, getting much closer to the speed of light.
What about their ionizing power? Less than alpha.
Much less. Maybe 1100th the ionizing power of an alpha particle over the same distance. They don't interact quite as violently, but still, about 100 times more ionizing than gamma rays.
Okay, moderate ionization and penetration. More than alpha.
Definitely.
Wow.
Moderate penetrating power. They can travel maybe a few meters in air, say around 5 meters. They'll pass through thin aluminum foil, but they'll be stopped by maybe 5 millimeters of aluminum.
And fields affect them too?
Yes. Being charged, they're deflected by electric and magnetic fields. And because they're much lighter and have the opposite charge to alpha particles, they get deflected more strongly and in the opposite direction.
Do they do other things like fluorescence?
Yep. They can cause fluorescence, affect photographic plates. An interesting one, When beta particles are stopped suddenly by hitting metal, they can actually generate X-rays.
Huh. And biologically, more dangerous than alpha in some ways.
Can be, yes. Because while alpha particles are stopped by skin, beta particles can penetrate the skin and deposit their energy into living tissue underneath.
Right. Okay, beta particles. Fast electrons, negative charge, moderate ionization and penetration. That leaves gamma. Totally different beasts, right?
Completely different. Gamma rays, rays, they're particles like alpha and beta. They're electromagnetic radiation, like light, like X-rays, but with much, much more energy and shorter wavelengths.
So, pure energy. No mass, no charge.
Exactly. Zero charge, zero rest mass. And they travel at the ultimate speed limit, the speed of light, 3 by 108 meters per second.
Wow. Okay, if they have no charge and no mass, how do they interact? Low ionization.
Very low ionizing power, yeah. Much less than alpha or beta. They don't interact as strongly through electrical forces or direct collisions. They tend to just pass through matter more easily.
But that means high penetration, right? They're hard to stop.
Extremely high penetrating power. They can travel hundreds of meters in air, pass through thick slabs of iron. To effectively stop gamma rays, you need really dense materials like thick lead shielding.
And electric or magnetic fields? No effect.
None at all. Since they have no charge, fields don't touch them.
But they do interact eventually, affect plates, cause fluorescence.
They still do, yes. They deposit their energy differently, but they can affect photographic plates, cause fluorescence, and like X-rays, they can be diffracted by crystals, which is how we can study their properties.
And biologically, sounds like they could be the most dangerous in some ways.
They are incredibly dangerous because they can pass right through the body, potentially damaging cells and DNA deep inside. But that same penetrating power makes them useful, paradoxically, in things like radiation therapy for cancer, where you need to target deep tissues.
Incredible. The properties are so distinct. Maybe we could just quickly summarize the key differences again, just nail them down.
Good idea. So, nature. Alpha is a helium nucleus particle. Beta is an electron particle. Gamma is electromagnetic radiation, wave photon.
Speed?
Alpha slowest, 107 meters.
Perhaps.
Beta faster, 108 meters. Gamma fastest, speed of light.
Mass?
Alpha heaviest, beta very light. Gamma zero rest mass.
Charge?
Alpha positive, plus 2e. Beta negative, e. Gamma neutral, 0.
Effective fields?
Alpha and beta deflected. Gamma unaffected.
Ionizing power?
Alpha highest, beta moderate. Gamma lowest.
Penetrating power?
Alpha lowest, stopped by paper. Beta moderate, stopped by aluminum. Gamma highest, needs thick lead.
Perfect. That really clarifies it. Okay, so these radiations come from the nucleus. What's actually happening inside the nucleus during these emissions, these nuclear transformations?
Exactly. Radioactive decay, at its heart, is about an unstable nucleus trying to become more stable. It does this by spontaneously spitting out one of these radiations, alpha, beta, or sometimes gamma, to reach a lower energy state.
Let's take alpha emission first. What changes when an alpha particle, 42 lasses, leaves?
Okay, an alpha particle contains 2 protons and 2 neutrons. So when a nucleus ejects one, the parent nucleus loses 2 protons and 2 neutrons.
So its atomic number Z goes down by 2?
Right, and its mass number A goes down by 4. This means the element actually changes into a different element, 2 places lower on the periodic table.
Wow, transmutation.
Exactly. The general equation looks like AZX right arrow A4Z2Y plus 42pH. A classic example is uranium-238 decaying into thorium-234Th plus an alpha particle.
Okay, alpha decay makes a new lighter element. What about beta emission? We said that involves a neutron turning into a proton.
That's the key. A neutron changes into a proton inside the nucleus. To balance the books, a beta particle, that electron, 011U, and an antineutrino are emitted.
So if a neutron becomes a proton, the number of protons goes up by 1.
Correct. The atomic number Z increases by 1. So again, the element changes, this time moving one place up the periodic table.
But what about the mass number A? A neutron became a proton.
So the total number of nucleons, protons plus neutrons, stays the same. The mass number A doesn't change in beta decay. The general form is AZP, right arrow, AZ plus 1Q plus 0, 1 plus bar nu.
Example.
Carbon-14 into nitrogen-14 at 27 at N is a very common one. Z goes from 6 to 7, A stays at 14.
Okay, beta decay also changes the element, but increases Z, keeps A the same. What about gamma emission? Does that change the element too?
Usually no. Gamma emission is typically like the nucleus calming down after an alpha or a beta decay. The daughter nucleus formed might be left in an excited high-energy state. We mark this with a little asterisk, like $6.
Okay.
To get down to its stable ground state, it releases the excess energy as a gamma ray photon. Since the gamma ray has no mass and no charge, Ejecting it doesn't change the number of protons or neutrons.
So Z and A stay the same.
Exactly. Same element, just less energetic. The equation is simple. AZX, right arrow, AZX plus gamma.
So gamma is more about energy release after the fact. And you mentioned it's usually either alpha or beta in a single decay step, maybe with gamma, but never alpha and beta together.
That's right. And these decays can happen in sequences, decay chains, where one unstable nucleus decays into another, which is also unstable, and so on, until eventually a stable nucleus is reached.
Okay, just to quickly recap the changes. Alpha emission. Z down by 2, A down by 4. Beta emission. Z up by 1, A unchanged. Gamma emission. Z unchanged, A unchanged.
Perfect summary. And these processes give us radioisotopes, which, despite being unstable, are incredibly useful.
Ah, yes, radioisotopes. So radioactive reasons of elements, often with, too many neutrons.
Often, yeah. Or an unstable configuration. We mentioned carbon-14, cobalt-60 is another big one, potassium-40, fonding AT, phosphorus-32, 15Pt4AC. Some occur naturally, others we make artificially in reactors or accelerators.
And we use them. How? Medicine seems like a big area.
Huge. Radiotherapy is a major one. Cobalt-60, for instance, emits powerful gamma rays. These can be precisely aimed at cancerous tumors to kill the cancer cells.
Using that penetrating power of gamma.
Exactly. It can reach deep inside the body. Then there are tracers.
Tracers.
Yeah, you tag a chemical compound with a radioactive isotope, say radiosodium chloride or radioiodine. You introduce a tiny, safe amount into the body.
And track where it goes.
Precisely. Specialized detectors outside the body can track the radiation. This helps doctors see how blood is circulating, find tumors or blockages, check organ function. It's a powerful diagnostic tool. Radiocardiology, for example, uses this to study the heart.
That's clever. Any other medical uses?
Sterilization. Gamma rays from sources like cobalt-60 are great for sterilizing medical equipment, syringes, bandages, implants. It's often quicker, cheaper, and more reliable than using heat, especially for heat-sensitive plastics.
Okay, medicine is covered. What about science? Basic research.
Well, alpha particles themselves from radioisotopes were used, as we said, to probe the atom. We still use particle beams generated in various ways to study nuclear structure and forces. In agriculture, tracers help scientists understand how plants take up nutrients from fertilizers or how pesticides move through the environment.
And carbon dating.
Can't forget carbon dating. Using the known decay rate of carbon-14 to figure out the age of old organic stuff. Bones, wood, cloth. Invaluable for archaeology and paleontology.
Right, thousands of years back. What about industry, day-to-day manufacturing?
Well, the big one is uranium-235 as fuel for nuclear power reactors, which we'll get to.
Okay.
But there are others. Radioisotopes can ionize air to prevent static electricity buildup on moving machinery parts, which can be a hazard.
Huh, neat.
They're used in luminescent signs. The radioactivity excites a phosphor, making it glow. Think exit signs. And thickness gauging.
How does that work?
You use the penetrating power of beta radiation. You put a source on one side of, say, a sheet of paper or plastic being made, and a detector on the other. If the sheet gets too thick, less radiation gets through. Too thin, more gets through. The detector signal controls the rollers to keep the thickness just right.
Very precise. Okay, so loads of uses, but radioactivity is, well, radioactive. It's dangerous. We have to talk about the harmful effects.
Absolutely crucial. Exposure to harmful levels of radiation can come from several places. We know about radioactive fallout from nuclear accidents. 3 Mile Island, 79. Chernobyl, 86. Fukushima, 20 low.
Okay.
Devastating event.
That's nuclear waste, the stuff left over from reactors.
Yes. Nuclear waste, especially spent fuel rods, is highly radioactive and stays that way for a very, very long time. Disposing of it safely is a massive challenge.
Are there other sources we encounter?
We get low levels from natural background radiation, cosmic rays, radon gas from the ground, radioactive elements in rocks and soil. And then there are man-made sources, like medical X-rays and radiation used in certain industrial processes or research accelerators.
What does this radiation actually do to us, biologically?
It interacts with the atoms and molecules in our cells. It can damage biological molecules, including DNA. This can kill cells outright or cause mutations.
What are the effects, short-term, long-term?
High doses, short-term exposure, what we call acute exposure, can cause radiation sickness. Nausea, vomiting, hair loss, diarrhea, damage to bone marrow.
Nasty.
Very. Long-term chronic exposure to lower levels increases the risk of developing cancers like leukemia years or decades later. And if the radiation damages DNA in sperm or egg cells, it can lead to genetic defects in future generations.
Are some parts of the body more sensitive?
Yes. Rapidly dividing cells are generally more vulnerable. so the bone marrow where blood cells are made, the lining of the gut, hair follicles, reproductive cells. Also, a developing fetus is extremely sensitive to radiation damage. The thyroid gland can absorb radioactive iodine specifically.
And different types of radiation pose different risks.
Broadly, yes. Alpha is dangerous if ingested or inhaled, but stopped by skin. Beta penetrates skin. Gamma and neutrons are highly penetrating and can cause damage deep inside the body, including direct DNA damage.
Okay, clearly safety is paramount. What kind of precautions are taken, especially around nuclear plants and handling radioactive materials?
Extremely strict protocols. Nuclear reactors are shielded by thick layers of lead and steel, enclosed in massive, airtight concrete containment buildings designed to withstand accidents or even external impacts. They have multiple redundant cooling systems to prevent overheating.
And for people working with this stuff?
Anyone handling radioactive materials uses shielding lead aprons, lead-lined gloves. They use remote handling tools like long tongs to maximize distance. And they wear dosimeters, film badges, or electronic ones to constantly track their accumulated radiation dose.
Where do they store the materials?
When not in use, radioactive sources are kept in thick lead containers, often with very narrow openings to minimize escaping radiation.
And the waste disposal, you said that's a challenge?
It is. The main approach for high-level waste like spent fuel is long-term isolation. The waste is sealed in robust casks, often made of steel and concrete, and then buried deep underground in stable geological formations, like granite or salt deposits, far away from people and water sources, or sometimes in sealed-off disused mines. The idea is to keep it contained for thousands, even hundreds of thousands of years, until it decays to safe levels.
That's a long time. You also mentioned background radiation earlier, the stuff we're always exposed to. Should we worry about that?
Background radiation is just part of living on Earth. It comes from space, cosmic rays, from the sun, from naturally radioactive elements in the ground, like uranium and thorium, which decay to produce radon gas. And even from within our own bodies, we all have tiny amounts of radioactive potassium-40 and carbon-14.
So it's unavoidable.
Pretty much. The levels vary depending on where you live, altitude, local geology, but for most people, the dose received from background radiation is well below levels considered harmful. It's generally not something to unduly worry about compared to concentrated sources or unnecessary exposures like too many medical x-rays.
Okay, good to know. Right, let's shift gears now to the energy side. Nuclear energy, it all comes back to Einstein, doesn't it? EMC day.
It absolutely does. That equation is the key. EMC 282. It tells us mass and energy are interchangeable. In nuclear reactions, like fission or fusion, the total mass of the products after the reaction is slightly less than the total mass of the reactants before.
A mass defect.
Exactly, the mass defect, delta MA. That tiny bit of missing mass hasn't vanished. It's been converted into a huge amount of energy, E, according to E delta M sine times CT2. And because C, the speed of light, is such a massive number, and you square it, even a minuscule amount of mass converts into a tremendous amount of energy.
Like how much?
If you could convert just 1 kilogram of mass entirely to energy, you'd get $9 times 10^6 joules. That's billions of kilowatt hours. An astronomical amount.
Wow. And we usually measure atomic masses in AMU, atomic mass units. How does that translate to energy?
Yeah, using AMU is convenient at the nuclear scale.
Yeah.
1 AMU is equivalent to about 931.5 megaelectron volts of energy. That's the conversion factor we use.
Okay.
So when we calculate the mass difference in a reaction in AMU, we can directly find the energy released in Meg. Just for context, a proton is about 1.00007 AM, a neutron slightly more, about 1.0009 AMU, and an electron is tiny, 0.00005 AM.
Got it. So this mass to energy conversion is what powers both fission and fusion. Let's dig into fission first, splitting the atom.
Right. Nuclear fission is when a heavy nucleus, typically uranium-235 or plutonium-239, absorbs a neutron, usually a slow-moving one. This makes the nucleus unstable.
And it splits.
It splits violently into two smaller nuclei, called fission fragments. Think barium and krypton as one possibility from uranium-235. But critically, it also releases a huge amount of energy, around 200 MeV per fission.
Wow, 200 MeV from one atom splitting.
And crucially, it also releases 2 or 3 more neutrons.
And that energy comes from the mass defect again. The fragments plus the neutrons way less than the original U-235 plus the incoming neutron.
Exactly. That tiny mass difference becomes the kinetic energy of the fragments flying apart at high speed, the energy of the neutrons, and also gamma radiation. The conservation laws hold total protons, and neutrons are the same before and after, but the total mass is slightly less.
And those released neutrons, that's the key to the chain reaction.
That is the absolute key. If you have enough fissionable materials packed together, like uranium-235, what we call the critical mass, then the neutrons released from one fission can go on to hit other U-235 nuclei, causing them to fission,
Releasing more neutrons.
which cause more fissions and so on. It can cascade very quickly.
An uncontrolled chain reaction.
That's a nuclear bomb, a massive, near-instantaneous release of energy.
But you can control it for power.
Yes. In a nuclear reactor, you control the chain reaction. You use control rods, often made of materials like cadmium or boron that absorb neutrons, to soak up excess neutrons, so that on average, only one neutron from each fission goes on to cause another fission,
Keeping it steady.
keeping it sustained and controlled. You also use a moderator, like water or graphite, to slow down the fast neutrons released by fission, because U-235 actually fissions much more effectively with slow neutrons. This allows you to extract the heat generated by the controlled fission and use it to boil water, create steam, and turn turbines to generate electricity.
So fission, destructive potential, but also constructive power generation. How is it different from radioactive decay, which also involves nuclear changes?
Good question. Key differences. Decay is spontaneous. Fission is induced, needs a neutron trigger. Fission releases vastly more energy per event than typical decay. And crucially, fission can lead to a controllable chain reaction, whereas decay happens at its own rate, determined by half-life, which we can't really control.
Okay, clear distinction. Now, the other side of the coin, nuclear fusion, combining light nuclei.
Yes, fusion is essentially the opposite process. You take two light nuclei, like isotopes of hydrogen, deuterium-21 and tritium-31 and force them together so hard they overcome their mutual electrical repulsion and fuse to form a heavier nucleus, like helium-42 Axis.
And energy is released here too.
A huge amount, yes. Again, it comes down to mass defect. The mass of the resulting helium nucleus plus any other particle released, like a neutron in the DT reaction, is less than the combined mass of the initial deuterium and tritium nuclei. That mass difference becomes energy.
What are some typical fusion reactions?
Well, fusing two deuterium nuclei, DD reaction, can happen in a couple of ways, producing helium-3 and a neutron, or tritium and a proton, releasing around 3,4 MeV. The deuterium-tritium DT reaction is a big focus for future power plants. 21H plus 31H right RO, 42 He, plus 10 millers. That one releases about 17.6 MeV.
And this is what powers stars, right? Fusion?
Absolutely. Stars are gigantic fusion reactors. In their cores, the immense gravity creates incredible temperatures and pressures, enough to fuse hydrogen nuclei protons into helium. The main process in stars like our Sun is the proton-proton chain, ultimately turning 4 protons into one helium nucleus, releasing about 27 MeV in the process. That's the source of sunlight and heat.
So fusion seems amazing. Potentially lots of energy, maybe cleaner fuel. Why aren't we using it for power now? What's the holdup?
The challenge is replicating those stellar conditions here on Earth. You need temperatures of millions of degrees Celsius hotter than the core of the Sun, actually, to get the nuclei moving fast enough to overcome their repulsion and fuse.
Millions of degrees? How do you even contain that?
Exactly. At those temperatures, matter isn't solid, liquid, or gas. It's a plasma. A superheated soup of charged ions and electrons. No physical container can hold it. So scientists are developing complex systems using powerful magnetic fields, like in tokamaks and stellarators, to confine the plasma, or using intense lasers or particle beams to rapidly heat and compress tiny fuel pellets. Inertial confinement.
Sounds incredibly difficult.
It is. Achieving sustained controlled fusion that produces more energy than you put into heat and confine the plasma, called ignition, is a massive scientific and engineering challenge. We're making progress with large international projects like ITER under construction, but commercial fusion power is likely still decades away.
So fission is working now, fusion is the long-term hope. How do they stack up overall? Energy release, fuel, waste.
Okay, energy per mass. Fusion actually releases significantly more energy per kilogram of fuel than fission. Fuel availability. Fusion fuels like deuterium are incredibly abundant from seawater, and tritium can be bred from lithium. Uranium for fission is more limited. Waste. Fission produces long-lived, highly radioactive waste. Fusion produces less waste, and it's generally less radioactive and decays much faster, although the reactor materials themselves can become activated.
But controllability.
Fission is a proven, controllable technology right now. Fusion is extremely difficult to initiate and sustain. Achieving controlled fusion is the main barrier. Also, while fission has been weaponized in atomic bombs, uncontrolled fusion is the basis of the much more powerful hydrogen bombs, ironically often requiring a fission bomb just to trigger them.
Wow. So much power, so many complexities. It really is incredible how everything connects. From the tiny particles in the nucleus to these immense energy releases, we've covered a huge amount today.
We really have, from the basic structure of atoms, isotopes, the discovery of radioactivity,
Alpha, beta, gamma radiation properties.
to nuclear transformations, decay, the many uses of radioisotopes,
Dangers, safety precautions, background radiation.
and finally, the principles of fission and fusion, the chain reaction EMC Asamaka, and the challenges and potential of nuclear energy. It shows how fundamental physics translates into technologies that profoundly shape our world.
It certainly does. So, as you, our listener, digest all of this, the immense power locked in the nucleus, the ways we harness it, the risks we manage, maybe take a moment to think. Consider the implications. We have life-saving medicine, the potential for vast clean energy, but also the responsibility of nuclear weapons and long-term waste. Looking forward, based on these fundamental principles, what future innovations, or maybe what ethical questions, does this powerful science bring to your mind? Something to ponder.